Welcome to the lecture series on CFD, Part 2. This is lecture 33 on examples of application of Reynolds-averaged Navier-Stokes equations. In this lecture, 5 examples of simulation of turbulent flows using Reynolds-averaged Navier-Stokes equations are presented. These examples are selected to show both the strengths and the weaknesses of Run's turbulence models. In the first example, a steady-state flow around an airfoil is studied. It is the same test case that was used in lecture 28 when solving the Euler equations, that is, assuming that the fluid is inviscid. We'll show how viscosity and turbulence change the solution. The second test case is flow in the mixer used in lecture 26, where the flow was assumed to be laminar, that is, the fluid was very viscous. The flow is unsteady, and the unsteadiness is imposed by the rotational motion of the impeller. Here we have to assume that ensemble averaging is performed, with one blade passing period being one member of the ensemble. If LES cannot be afforded, an unsteady Run's approach can be used in such cases. The third example is the flow around an airplane wing at different angles of attack. The aim is to predict drag and lift variation with the angle of attack and find out when the stall happens. In the fourth test case, turbulent flow around a sphere at different Reynolds numbers is computed. This is the kind of flow for which none of Run's turbulence models performs well. The fifth test case is devoted to turbulence-driven secondary flow in a duct with a square cross-section. Here we demonstrate that linear eddy viscosity types of models cannot predict such flows, while Reynolds stress models can. In lecture 28, two-dimensional compressible flow around an airfoil was studied using the Euler equations, that is, assuming that fluid is inviscid, which corresponds to an infinite Reynolds number. Here we present the results from computations using Run's equations for flows at Mach number equal to 0.6, that is subsonic flow, and 0.8, that is transonic flow, and compare them with solutions of the Euler equations. At Mach number equal 0.6, the Reynolds number based on chord length, c equal 1 meter, free stream velocity, u equal 208.4 meters per second, air density, rho equal 1.176 kilogram per cubic meter, and dynamic viscosity, mu equal 1.855 times 10 to minus 5 Pascal seconds, is about 13.2 million. At Mach number equal 0.8, the Reynolds number is circa 17.6 million. At Mach number equal 0.6, the grid was the same as for the Euler equations. It will be shown in the next slide. At Mach number equal 0.8, the grid had to be changed because the position of shocks has changed compared to inviscid flow. The turbulence model was the default version of the K-epsilon model in the SimCenter Stasis Simple software, with wall functions applied at wall boundaries. We consider first the subsonic flow at Mach number equal 0.6. This plot shows the polygonal grid around the airfoil, which is locally refined in airfoil vicinity. These plots show grid details around the leading edge of the airfoil on the left and around its trailing edge on the right. The theoretical airfoil profiles have a sharp trailing edge, but in practical applications a finite thickness is used for manufacturing and handling reasons. 8 prism layers along airfoil wall are created, which is suitable when wall functions are used. Note that prism layers are made thinner near leading and trailing edges, which will result in lower y plus values, as will be shown in slide 8. These 4 plots show Mach number, pressure, temperature, and density variation around the airfoil. When comparing this slide with slide 24 of lecture 28, we see that the solutions are similar away from airfoil. However, we see here that a boundary layer is formed near airfoil wall and is getting thicker toward the trailing edge, while there is no boundary layer at all in inviscid flow solutions. The effect of the wall boundary layer is visible in the wake as well. This plot shows the distribution of Y plus along airfoil. Except near the front stagnation point where the velocity tends to 0, Y plus is in the range between 30 and 90, which is acceptable when both functions are used. Note sudden drops in Y plus at these locations, which correspond to locations where prisma layers in the grid were made thinner. These two plots show contours of turbulent kinetic energy and turbulent viscosity around the airfoil. Both quantities have non-zero values only in the boundary layer and in the wake, where viscous effects are important. Further away from wall, they are negligible. Turbulent viscosity has maximum values in the wake near trailing edge, where it is about 1,600 times higher than fluid viscosity. This plot shows the comparison of pressure variation over airfoil surface computed for inviscid and turbulent flow. At the first sight, differences do not appear large, but a closer look reveals that in a turbulent flow, pressure is lower on pressure side and higher on suction side than in inviscid flow, which leads to a lower lift, 0.582 versus 0.69 in inviscid flow. See slide 26 of lecture 28. This plot shows the comparison of pressure variation over airfoil surface computed using sequential and coupled solver in SimCenter Stasis Simple software. The two solvers use slightly different discretization methods, but the results are almost identical. These two plots show convergence of drag and lift coefficient with iterations in the computation using sequential solver. The values become practically constant after about 900 iterations. This plot shows the distribution of friction coefficient, that is, the normalized shear stress along the airfoil surface. Shear stress is higher on suction side than on pressure side because velocities near wall are higher there, except near leading and trailing edge. These loose dots correspond to the blunt part of the trailing edge. The two plots on the right show residual histories from computations with sequential and coupled solver. Under-relaxation factors in the sequential solver were 0.1 for pressure and 0.9 for all other variables. The stepping in pseudo time in coupled solver corresponds to the CFL number of 1000. These settings were not optimized for efficiency. Residuals for continuity, momentum, and energy equations reduce much faster in the coupled solver, which is more efficient than sequential solver in subsonic flows. Residuals for turbulence model variables stall at a low enough level in both solvers. This was not further investigated, but the most likely cause is the use of second-order discretization for convection and the actions of gradient limiters. The results are not affected because the residuals were reduced by 4 orders of magnitude before stalling. We now turn to transonic flow at Mach number equal 0.8. This plot shows the grid around the airfoil. It is similar to the grid used for Mach number equal 0.6, except for local refinements in zones where shock waves are expected. Because the position of shocks is not exactly known in advance, the refinement stretches over a wider zone than necessary. A more economical way is to use solution adaptive grid refinement, which will be the subject of lecture 38. The shock adapted grid for this particular case is shown in slide 15 of lecture 38. Computations were again performed with both sequential and coupled solvers in SimCenter Stasis Simple software. Iterations did not converge to a steady state with either solver, with any set of parameters tried. Computations in unsteady mode converged well within each time step, as shown in these two plots for both solvers. As will be shown in slide 15, the unsteadiness is relatively weak. To find out whether it is physical or caused by some numerical effects would require deeper analysis and parameter variation, which was not done here. Second-order discretization and limiters applied at shocks are the potential causes of numerical instabilities. These 4 plots show Mach number, pressure, temperature, and velocity variation around the airfoil. When comparing this slide with slide 28 of lecture 28, we see that the solutions are highly different. The position and the shape of shocks are different, and the maximum value of Mach number is lower in the case of turbulent flow, 1.43 versus 1.66 in inviscid flow. Note also the existence of a recirculation zone behind the shock on suction side, contrary to flow pattern at Mach equal 0.6 and to inviscid flow pattern. These two plots show contours of turbulent kinetic energy and turbulent viscosity around the airfoil. Both quantities have non-zero values only in the boundary layer and in the wake, where viscous effects are important. Further away from the airfoil and its wake, they are negligible. Turbulent kinetic energy is maximum in the shear layer above the recirculation zone. The maximum turbulent viscosity is found in the wake downstream of the trailing edge, where it is more than 25,000 times higher than fluid viscosity. This plot shows the variation of Y plus over the airfoil surface. Except immediately at the leading edge, the values range between 40 and 110, which is appropriate when wall functions are used. This plot shows the variation of friction coefficient, that is, normalized wall shear stress, over airfoil surface. The locations of the two shocks are clearly visible because of a sudden reduction of velocity across shocks. This plot shows the comparison of pressure variation over airfoil surface computed with sequential and coupled solver in SimCenter Stasis and Plus software. The results differ slightly in the position of shocks, but this may be due to the fact that shocks move slightly hence and forth in the unsteady simulation, and the plots represent an instantaneous solution. This plot shows the comparison of pressure variation over airfoil surface computed for inviscid and turbulent flow. Contrary to the case of subsonic flow at Mach number equal 0.6, differences are now very large, especially in the position of shocks. In turbulence flow, pressure is lower on pressure side and higher on suction side than in inviscid flow, which leads to a lower lift, 0.259 versus 0.867 in inviscid flow. These two plots show the variation of drag and lift coefficient over time in the computation using sequential solver. The values become nearly constant after about 0.2 seconds, but a small variation remains present. In lecture 26, laminar flow in a mixer was studied using a moving grid attached to the impeller with a sliding interface to the fixed grid attached to the vessel wall and baffles. Here we present results from the computations of turbulent flow in the same geometry and with the same grid, using Run's equations and the K epsilon turbulence model. Outer vessel diameter is 100 mm and its height is also 100 mm. Fluid density is 1000 kg per cubic meter and dynamic viscosity is 0.001 pascal second, which is 100 times lower than in laminar flow studied in lecture 26. Impeller rotation speed is 600 rpm or 10 revolutions per second, which is 10 times faster than in laminar flow from lecture 26. The Reynolds number is thus 1000 times higher, which leads to the flow being turbulent. The time step was set to 0.2 milliseconds, which corresponds to 500 time steps per rotation period of 0.1 second or 0.72 degrees rotation per time step. Second order discretization is used in both space and time. These two plots show sections through the polyhedral grid, vertical section along the shaft on the left and a horizontal cross section through the impeller on the right. The rotating region attached to the impeller and the fixed region attached to the casing and baffles are separated by a cylindrical sliding interface. Prism layers are generated along all walls. The grid is finer near impeller blades than elsewhere, which was achieved by specifying a smaller cell size for impeller surface. This plot shows residual histories over the last 16 time steps. Residuals are reduced by circa 2 orders of magnitude within each time step and jump to the same initial level at the beginning of each new time step. These two plots show variation of torque and thrust on impeller over time. After circa 0.5 seconds, corresponding to 5 impeller rotations, a nearly periodic variation of torque is obtained, while the thrust becomes nearly constant. Because the impeller has 4 blades, and there are also 4 baffles on the casing, we see 4 periods of torque oscillation per impeller rotation. This plot shows the variation of torque on stator blades over time. The variation is periodic with the same blade passing frequency as on the impeller, but the amplitude of oscillations is much higher. This slide shows animation of velocity on the left and pressure on the right in the section plane through stator baffles and impeller shaft. The rotating impeller blades are pushing fluid downward and sucking from above, thus creating counter-rotating vortexes below and above impeller. These vortexes are stable but move to some extent during each blade passing period. The pressure is high on the downward side of impeller blades and low on the upward side, as expected. Because impeller blades are inclined, they push the fluid not only toward mixer bottom, but also toward the cylindrical casing. This is why we see high pressure in the impingement zone on fixed walls. This slide shows animation of velocity vectors on the left and pressure variation on the right in the horizontal cross-section through the impeller. Velocities are highest near impeller blades and lowest in corners along fixed baffles. Pressure is high on the front side and low on the rear side of impeller blades relative to their rotation direction. In a coordinate system attached to impeller, the flow within the rotating region is almost steady, except for disturbances when passing the fixed baffles. This is sometimes used as an argument for a steady state computation in multiple frames of reference. However, this approach introduces modeling errors which can be significant and should therefore be used with care. This slide shows instantaneous distribution of turbulent kinetic energy in the section plane through stator baffles and impeller shaft on the left, and in a cross-section through the impeller blades on the right. Turbulent kinetic energy is very low near shaft, bottom, and top of the mixer. Highest values are found around blade tips, especially when they are passing fixed baffles. The horizontal section also shows increased turbulent kinetic energy in the wake of each blade. This is obviously not an optimal mixing device. For better mixing, the turbulent intensity should be higher in the whole mixer. This slide shows instantaneous distribution of turbulent viscosity in the section plane through stator baffles and the shaft on the left, and in a cross-section through the impeller on the right. Peak values in shear layers and blade wakes are around 1430 times higher than fluid viscosity. This slide shows results of simulation of flow around a wing body assembly, which was the subject of one AIWA workshop. The diagram shows the comparison of predicted using SimSet star CCM Plus and measured lift coefficient as a function of the angle of attack. The agreement is very good up to the angle of attack at which the maximum lift is obtained. Beyond this point, the tip vortex becomes thicker and it starts propagating along the wing toward the body. This leads to stall, a massive separation on the wing suction side, which results in a sudden drop of the lift force. In aircraft design, it is very important to know the limiting angle of attack beyond which the stall can happen, because this is a dangerous situation which can lead to aircraft crash during landing. Simulation based on RANS models usually predict stall a few degrees too late. We now turn to a more detailed analysis of flow around the sphere. In lecture 31, we have seen that LES produces reasonably good prediction of flow around the sphere, provided that the grid resolution is sufficient for the Reynolds number studied. RANS approach produces poor results for all subcritical Reynolds numbers with any turbulence model, the drag is severely underpredicted. In the supercritical range of Reynolds numbers, after the drag crisis, one would expect a better performance of Run's models. However, the results are still not very good, as will be shown in the following slides. We performed computations for the same geometry studied in lecture 31, only the Reynolds number was increased by a factor 10 to 500,000 by increasing the density. 4 turbulence models we tried in Simpson Testacisian plus software. Standard K-epsilon model with low ray wall treatment, which converges to a nearly steady state. Like EB K-epsilon model with low ray wall treatment, which also converged to a nearly steady state. Mentor's SST version of K-omega model with low ray wall treatment, which also converged to a nearly steady state. And a Reynolds stress model with elliptic blending, which did not converge to steady state. This slide shows the locally refined trimmed grid around the sphere with a diameter of 61.4 millimeters, a billiard ball, and the stick with which the sphere was held during experiments in a wind tunnel. The grid had 5.87 million cells. In this zone near sphere, the cell size was 0.625 millimeters, which is slightly more than 1/100th of the sphere diameter. 2 more levels of refinement were applied near sphere surface. Along sphere wall, there are 16 prism layers, with the thickness of the layer next to wall being 5 micrometers. All prism layers extend to a distance of 1 millimeter from the sphere wall. This arrangement is needed to achieve low enough Y plus values so that no wall functions are used. Residuals could not be reduced beyond certain limit with any Run's model. With Reynolds stress model, residuals oscillated at a high level and thus no usable steady-state solution was obtained. With the other 3 models, residual levels could be reduced by 3 to 4 orders of magnitude, but not more. Oscillation of residuals at a low level can be tolerated if it is certain that quantities of interest are not changing significantly with iterations. With SST K-omega model and leg EB K-epsilon model, simulations were also continued in unsteady mode, with 5 auto iterations per time step. With SST K-omega model, transient simulation did not lead to a significant variation in forces on sphere. The solution was almost steady. With leg EB K-epsilon model, the forces oscillated with a small amplitude and a long period. This slide shows the distribution of Y plus over sphere and stick surface from transient simulations with SST K-omega model in the upper plot and leg EB K-epsilon model in the lower plot. The line of flow separation can be recognized by the lowest Y plus values because the velocity is very low near separation line. The Y plus values exceed 1.0 only in a narrow band, and therefore the low ray treatment is justified, that is, no wall functions are used. The solution obtained with leg EB K-epsilon model is almost axisymmetric. However, the solution obtained with the SST K-omega model is symmetric in the plane Y equals 0, but not in the plane Z equals 0. This will be shown in the next slide. This slide shows the flow pattern in 2 coordinate planes, Y equals 0 in the upper plots and Z equals 0 in the lower plots, from computations with the SST K-omega model, left plots, and leg EB K-epsilon model in right plots. We see that the flow separation takes place earlier and leads to a larger recirculation zone with the K-omega SST model than with the leg EB K-epsilon model. We can also see that the flow is nearly axisymmetric in the solution obtained with the leg EB K-epsilon model, while the solution from the SST K-omega model is nearly symmetric in the plane Y equals 0, but highly asymmetric in the plane Z equals 0. A similar solution was also obtained with a polyhedral grid. This slide shows the pressure distribution in 2 coordinate planes, Y equals 0 in the upper plots and Z equals 0 in the lower plots, obtained with SST K-omega model in the left plots and leg EB K-epsilon model in the right plots. The minimum pressure on sphere is found before equator in the SST K omega model solutions, while it is at the equator in the leg EB K epsilon solutions. The pressure distribution is nearly axisymmetric in the solution obtained with the leg EB K epsilon model, while the solution from the SST K omega model is symmetric in the plane y equals 0, but highly asymmetric in the plane z equals 0. This slide shows the turbulent kinetic energy distribution in two coordinate planes, y equals 0 in the upper plots and z equals 0 in the lower plots, from computations with the SST K omega model on the left and leg EB K epsilon model on the right. The maximum values are much higher when the SST K omega model is used than with the leg EB K epsilon model. The distribution is nearly axisymmetric in the solution obtained with the SST K omega model in the plane y equals 0, while it is highly asymmetric in the plane z equals 0. The solution is slightly asymmetric in both planes with the leg EB K epsilon model. This slide shows the turbulent viscosity ratio distribution in two coordinate planes, y equals 0 in the upper plots and z equals 0 in the lower plots, from computations with the SST K omega model on the left and leg EB K epsilon model on the right. The maximum values are much higher when the SST K omega model is used than with the leg EB K epsilon model. The distribution is nearly axisymmetric in the solution obtained with the SST K omega model in the plane y equals 0, but it is highly asymmetric in the plane z equals 0. The solution is slightly asymmetric for both planes with the leg EB K epsilon model. This slide shows the variation of drag on the left and lift coefficients on the right with time in the simulation with leg EB K epsilon model when unsteady simulation is continued from the non-converged steady-state computation. The period of drag oscillation is about 0.25 seconds, which corresponds to 50t, where t is equal d over u, which is the time fluid needs to travel the distance d, and d is the sphere diameter. The period of lift oscillation is twice as long. The amplitude of drag oscillation is small, less than 0.7% of the mean value. Simulations were also performed on two coarser grids, with cell size and time step increased by a factor 1.5 to assess the grid dependence. The results are shown on the next slide. These two plots show the variation of the drag coefficient with time in the simulation with leg EB K epsilon model on medium on the left and coarse grid on the right. The simulation on each grid was continued from the simulation on the next finer grid. The period of drag oscillation is shorter and the amplitude is higher on coarser grids, but the mean values do not change much. 0.079 on the coarse, 0.0777 on the medium, and 0.0744 on the fine grid. This table shows the comparison of drag and lift coefficients computed with free turbulence models on the fine grid. Lift coefficients oscillate around 0 with K epsilon models, but the SST K omega model predicts a steady lift in y direction with 0 lift in z direction. The drag coefficient predicted with K epsilon models is not too far from experimental data, about 10%, but the value from the simulation with K omega model is far too high. The last test case is devoted to turbulence-driven secondary flow in a duct with a square cross-section. In ducts with a non-circular cross-section, turbulence causes secondary flow which pulls fluid into corners. Linear eddy viscosity type turbulence models, like K epsilon, K omega, cannot predict this feature. Reynolds stress models and some nonlinear eddy viscosity type models can. The duct cross-section is 0.1 meter by 0.1 meter, and its length is also 0.1 meter. Fluid density is 1000 kg per cubic meter, and its dynamic viscosity is 0.001 Pascal second. Periodic conditions at inlet and outlet are used with a prescribed flow rate of 50 kg per second. This results in the mean velocity in the duct of 5 meters per second and the Reynolds number of 500,000. The cell size in the cross-section plane was uniform, 0.625 mm by 0.625 mm, corresponding to a resolution with 160 by 160 cells. In flow direction, 10 cells were created. Because of the assumption that the flow is fully developed, there is no variation of variables in the flow direction other than a linear variation of pressure. This slide shows contours of the streamwise velocity component, secondary velocity vectors, and contours of turbulent kinetic energy in a duct cross-section, computed using the K-epsilon model in the upper plots and the Reynolds stress model in the lower plots. The secondary velocity vectors computed with the K-epsilon model have no real meaning. They are at the round-off level. The Reynolds stress model predicts correctly secondary velocity vectors pointing along diagonals toward duct corner, thus creating 8 secondary vortices. The maximum secondary velocities are greater than 2% of the mean streamwise velocity. The secondary velocities lead to a more uniform distribution of the streamwise velocity component in the cross-section and thus a lower maximum value, 5.7 meters per second in the solution obtained with the Reynolds stress model compared to 5.838 meters per second in the solution obtained with the K-epsilon model. The contours of turbulent kinetic energy are totally different. While the K-epsilon model predicts peak values near duct corners, the Reynolds stress model predicts low turbulent kinetic energy there, with peaks located at the centers of each side wall. This slide shows the distribution of normal in the upper plots and shear components in the lower plots of Reynolds stresses predicted using the Reynolds stress model. Note the anisotropy and coordinate invariance of Reynolds stresses. The U squared is twice as large as V squared or W squared, and the shear stresses UV and UW are the same, only rotated by 90 degrees. If the coordinate system is rotated by 90 degrees, the solution would look the same, only V and W will be interchanged. Here is a summary of this lecture. Solutions of Run's equations do not always converge to a steady state. Assuming that no user errors are involved, the reason is usually the inherent unsteadiness of the flow, like vortex shedding or shear layer instability. Transient simulation may lead to a nearly steady state solution if the unsteadiness is weak, as was the case with the transonic flow around an airfoil. Unsteady runs, often called U-runs simulations, can be employed for flows with unsteady forcing, like the mixer example with a rotating impeller in slides 16 to 22. Turbulence models for Run's equations usually have problems with flows involving transition from laminar to turbulent state, like subcritical and critical flows around sphere and cylinder, and in general with predicting separation from smooth surfaces. Linear eddy viscosity types of Run's turbulence models cannot predict turbulence-driven secondary flows in ducts of non-circular cross-sections. For such flows, Reynolds stress models or nonlinear versions of eddy viscosity models should be used.